on Monday. What's the function that happens on Monday?
It's like the concert.
In order to accommodate that, we are going to have a somewhat shorter test. I'm such a pushover. But what is on truth tables, going back and forth between truth tables and logic tables for sure. So I'll give you a truth table and actually do a logic circuits. One of my logic circuits is ask me to create a truth table. Okay? Gates. I might talk about say, what's the output of? Remember the flip-flops? We had the little chart. The chart. Yeah. I'll give you one of those. So I'll give you one flip-flop chart. And remember we have two types of flip-flop, or actually several types of flip-flop charts. And I'll tell you which one. I can pretty much guarantee it's going to have, there'll be like an enable switch. Pretty much guarantee you that. Yes, I would expect also I'll have set reset. No, I should do it right classes either. All of my tests are next Monday and Tuesday, so treat them all the same. Fairness for everyone. Chronoff maps. No assembly language on Monday, none whatsoever. Zero, nada, zilch. And I realized I may have made a mistake on Monday by even starting that too soon, but what we're going to do is we're still going to do assembly today, but we're going to do it in a very low impact. However, I'll pretty much hit you next Wednesday next week. We're going to have to, and what I'm going to do is send out an announcement over the weekend about exactly how to set up your computer and all that kind of stuff so you're ready for next Monday. We really need to hit the road running next Monday. Does anybody have any idea of how many classes we have left here? This is week 9. And after we finish next Monday is our test. After that, we have like 10 classes left. Yeah, probably 8 because we have another test. And we have Thanksgiving.
That's the last day of class.
Yeah. So that's December 1st. So we're starting to run out of time. So
It says 13.
do we have 13 classes left?
Yeah.
From today?
I mean, that's also including our final and our third test.
Oh, yeah.
Right.
11.
And Monday, second test. I don't even think.
I counted that. So I guess 10.
Okay, so we're so what we got to do is we got to hit the road running on the assembly stuff. So I'm going to send you out an announcement over web courses. Anyway, today we're going to do a low impact version of assembly, and we're actually going to see some videos where people are actually doing less intense things than me. So that will kind of give a more gentle introduction to this. And then, as I said, next Wednesday will be great tests. Okay? So that's how we're doing it. And next Monday, theoretically next Monday, and if this doesn't happen, I'll be in trouble. Theoretically next Monday, it'll be done in 40 minutes, 40 or 45 minutes. Okay.
Okay, g'day all. Welcome to
G'day all.
2014. How's that?
That about.
Happy New Year, everybody. Okay, so today I thought I'd do something just a little bit fun. This is a top 20 x86 instructions for every program should know.
We have fun and
I
stuff.
love watching those top 20s on YouTube or the TV. I don't know why. They seem really fun to so I thought I'd make a top 20 of x86 instructions. Now, every program doesn't need to know these. Obviously, there's excellent programmers out there that have no idea about any assembly. So, yeah, this is mostly just people that debug C++. Or otherwise need to know machine code or assembly. Maybe you're an x86 programmer yourself. I don't know. But there's well over 500 instructions in a modern x86 CPU, so the instruction sets nowadays are just amazing. These are CISC or CISC, complex instruction set computing CPUs, and if you disassemble a program, this is usually against the EULA, so yeah, maybe read the EULA first before disassembling a particular program, or code something yourself and disassemble that. But if you do, if you disassemble an EXE, what you'll see isn't a stream of random 500 plus instructions. What you'll see is actually just a handful of instructions over and over again. These are the top 20 x86 instructions, and most of the code nowadays, most of the machine code nowadays, probably about 95%, is composed of nothing but these 20 x86 instructions. So they're super, super important. And if you're just learning x86 assembly and you're wondering where to start, you know, don't sit down and try and learn all 500 of the x86 instructions. What you really want to do is just learn these 20. Okay, yes, I just made this list up. And the order as well, you know, they're very, very important instructions. The order's not particularly important, but I have tried to put some order to these instructions. If you want an idea of the frequency of x86 instructions, what you want to do is check out this website just here, made by a fellow called Peter. Have a look at that. So he's done some stats on disassembled EXEs, and he's composed a list of the most common 20 x86 instructions. But this list that we're about to go through is not actually based on the above, and I made this list before I actually read that website. Anyway, have a look if you want. So there's also a glaring omission in my list, and that's that this is not about floating point. Yeah, we're not talking about x87 or SIMD here, we're just talking about the basic x86 instruction set. And there's a really good reason for that too. Okay, on to the list itself. Number 20, coming in at spot number 20, shift left. Alright, this is a really important instruction. So short is the mnemonic. It shifts all of the bits of the first operand left by the amount specified in the second. So that second operand there can either be an immediate 8-bit value, or it can be CL. So if you want to shift left by a variable amount, you've got to use CL register. And shift left is really famously used. I say famous, I don't know how famous it is, but it's really commonly used to multiply an operand by powers of 2. So shift left EAX by X bits is the same as saying multiply EAX by 2 to the power of X. Yeah. For instance, to multiply by 2 to the power of 5, you do short EAX and 5. Or you might want to multiply BX by 2 to the power of whatever's in CL. That was short BX CL. Shift left. Okay, good stuff. And the next one, number 19, shift right. I don't know how I decided that shift left was number 20 and shift right was 19, but that's just what I've done. So shift right is the opposite of shift left, and it's used to multiply, or sorry, to divide numbers by powers of 2. And there's actually 2 versions of shift right. There's just sure, or shift right, and there's also shift arithmetic right, or SAR. And what you want to do, if you want to divide an unsigned number by a power of 2, you use SHR, and if you want to divide a signed number by powers of 2, you want to use SAR, shift arithmetic right instead of sure. But it's pretty much the same, or the exact opposite of shift left. So if you want to divide, say, EAX by 2 to the power of 14, what you do is SHR, EAX, and then 14. Just like shift left, if you want to use a variable as your second operand there, the number of bits to shift, then your only option is CL. Strangely enough. I don't know why they chose that, but that's just the way it is. And then here's an example of SAR. So, yeah, just remember that SAR is for signed division, and SHR is for unsigned. Good stuff. Shift left, shift right. Alrighty, coming in at 18 is divide itself. So divide, there's 2 versions. There's div and idiv. It's used to divide integers, of course. Div is for unsigned integers, and idiv is for signed integers. And it's interesting, it's really useful actually, but these instructions actually return the quotient or the result of the division, but they also return the remainder of the division as well. You want to be careful and use them wisely, since div and idiv are really slow. they're among the slowest of all the instructions in the x86 instruction set. Like there are some that are really, really complicated, that take a lot more time, something like CPU ID. But divide and ID are really, they're up there for being the slowest instructions of all. You can, if you want, use SHR and SAR, shift right, instead of div. Yeah, whenever you can actually. So if you've ever got to divide by a power of 2, you want to use shifts instead of div. The operand is actually the divisor. Yeah, the operand that you give here is the divisor, and it specifies the size of the dividend and where the results should be stored. So this is really awkward, actually. It's really awkward. But if you want a simpler way to divide numbers, you might want to look at SC. That's got a bunch of division instructions. They're quite important, but yeah, it might be more convenient than using div or ID. Anyway, the operand size. So if your operand is 8 bits wide, then the dividend is implied, the quotient and the remainder, they're implied as well. The dividend will be seen as AX, and the quotient will be placed in AL, and the remainder in AH. Or, and this is where things get a bit weird, if your operand size is 16 bits, then your dividend is seen as the 32-bit combination or composite register DX, AX. So DX there would be the high bits, and AX would be the low 16 bits of your dividend. And the quotient will be stored in AX in that case, and the remainder in DX. And that pattern sort of continues there, using RDX and RAX as the dividend if your operand is 64 bits in size. Which is pretty interesting, really, because that means that RDX and RAX are really a gigantic 128-bit register. Yeah, but your quotient will be stored in RAX and your remainder in RDX. Yeah, integer division, div and I. Okay, so the opposite of division is, of course, multiplication, and we've got a bunch of these too. So mul is used for unsigned multiplication, and imul is used for signed multiplication. And I decided to put multiply as number 17 in my amazing list. So these are the multiplication instructions. Mul is unsigned, imul is signed. There's only one version of mul. The only way to do mul is a single operand version. But imul has a few convenient other versions. So you've got a 2-operand version of imul, and you've also got a 3-operand version of imul. The 2 and 3-operand versions of imul are much more convenient. So the 2-operand version of imul actually multiplies both numbers together and stores the result in the first operand. And the 3-operand version of imul multiplies the second operand by the immediate 8th operand and stores the result of that multiplication in the first operand. If you're using the single version, the single operand versions of mul or imul, this is what you're going to get. So it's similar to the division instructions. Yeah, the size of the operand specifies the implied second operand, and it also specifies where the resulting high and low bits are going to go. Yeah, so if you multiply an 8-bit operand, you can obviously get a 16-bit result from that. What's going to happen is the implied second operand is AL, and the resulting high bits are going to be stored in AH, and the resulting low bits in AL. So basically, if you multiply an 8-bit operand, then your result is going to be in AX. Things get a little bit weird if your operand is 16, 32, or 64 bits. Once again, your implied second operand is going to be the appropriate version of RAX. So it's going to be AX for 16 bits, EAX for 32 bits, or 64 bits to be RAX. And the resulting high bits are going to be stored in, the appropriate version of DX. So that's where things get a bit weird. And your resulting low bits are going to be stored in the resulting version of AX, or the appropriate version of AX. So this is kind of building those composite registers. So DX, AX acts as a single register here, with DX being the high 8 bits, 16 bits, sorry, and AX being the low 16 bits. It's a little bit weird, it takes a bit of getting used to, and like the same as division, if you want a slightly more convenient way to multiply numbers, you might want to think about using SC. Anyway, number 17 is multiply. Alright, number 16, the call instruction. This is really, really important. So call is used to call a subfunction. It actually pushes the current value of the IP, which is the instruction pointer, or PC, I think, other architectures might call it, the program counter. We call it IP in x86. it pushes that onto the stack and it moves the IP to whatever the parameter is. So this could be just a function name, it could be a label, it could be a register if you want. But the IP is actually a special register which points to the next instruction to be read and executed by the CPU. So when we change the IP, what's going to happen is the CPU is going to start reading and executing instructions from the function. Yeah, you can start. Okay, so once you call a subfunction, at some point you're probably going to want to return. So ret, short for return, returns from the function, usually after a call instruction. So what this instruction actually does is pops the original value of the IP back into the IP. So if you remember, that call pushes the IP and then jumps to some other part of the code. Ret pops the IP back into, or pops from the stack back into the IP. So the CPU actually continues executing from where it was before the call instruction. So ret is actually used to return from a function call, but all it actually does is the otherwise illegal pop IP. Yeah, you can't type pop IP, and it's not an instruction, but ret is exactly the same as pop IP. Okay, so number 14, here's some stack operations. We've got push. Push is used to save the value to the stack so that it can later be popped or used as a parameter to a function. The stack pointer, RSP it's called, is decremented and the operand's value is copied to the top of the stack. Now, push is really, really important. It's used all over the place. Like I said, it's used to pass parameters to functions, but it's also used just to save values of registers temporarily. So maybe if you want to use something non-scratch in your function, maybe you want to use RBX, for example, you might want to push the value to the stack before you use it, because C++ is going to expect that RBX is not changed. So you want to push those non-scratch registers if you use them in your function, and then at the end of your function, just before ret, you want to pop them back into the registers again, so that C++ doesn't get confused. Push. Okay, number 13, pop. So number 13, pop is only slightly more important than push. I don't know why I put them in that order. But pop is used to pop values previously pushed to the stack. Yeah, super, super important. Really, you can't only pop without push, and you can't only push without pop. So 14 and 13 are pretty much push and pop. Doesn't matter what order you're doing. Well, it doesn't matter what order I put them in, but pop actually copies the value from the stack and increments the stack pointer again, so that it points to the next value to be popped. And push and pop are really important for quickly saving temporary variables on the stack, which includes saving the values of those non-scratch registers, like I mentioned before. And what you want to remember is that the stack is a stack. You know, that's the data structure that it is. And if you look up stack on Wikipedia, you'll learn that stacks are all about popping things in the opposite order so they'll push. Yeah, so do be careful to get that right, otherwise it'll be embarrassing. Alright, number 12, here we go, onto bitwise not. Okay, so this is a really cool instruction. It actually flips all of the bits in your operand. So if you pass it a register, say RAX, if you not RAX, what it's going to do is it's going to flip all of the zeros to ones and all of the ones to zeros, working on binary bits there. So this doesn't actually negate a signed integer. If you're new to assembly or you've not really looked at the way that x86 CPUs represent negative numbers, this might be a point of confusion. What you want to do, if you want to negate a signed integer, you want to use neg instead of not. Yeah, so not performs what's called the ones complement, and neg performs the twos complement. And x86 CPUs generally represent signed numbers with twos complement. Anyway, bitwise not, number 12. Okay, number 11, increment, or inc. Increment adds 1 to an operand. So, yeah, we give it a register, say RAX, inc RAX is going to add 1 to RAX. It's a bit weird, but it doesn't set the carry flag. So if you want to do an int which sets the carry flag, what you want to do is the functionally equivalent add, and then your operand, and then 1. This is it's just strange. I don't know why they do this. I think it's got something to do with the loop instruction. Yeah, if you ever look up the loop instruction, you'll see that it does weird things with inc. Anyway, that's why I thought they did it like they did, but inc doesn't set the carry flag. Okay, and the next, here we go, the top 10 now. So number 10, decrement or dec. Dec is the opposite of inc. Instead of adding 1 to an operand, it subtracts 1. And just like inc, it doesn't set the carry flag. So if you want to perform a dec, which sets the carry flag, what you want to do is sub. Sub 1 from the old dec is, I'll put dec here actually as 10 and inc as 11 because dec I think is slightly more common, maybe, I don't know. But dec is often used as the tail of a loop with J and Z or jump not 0 because it's faster than the loop instruction. The loop instruction does have its own tricks up its sleeve, so if you're interested, go and check it out in the AMD or Intel manuals. Yeah, the loop's pretty interesting as well, but it is slower. So this is something that you'll see. This is where dec is used really, really commonly. You'll see a loop, so my loop, colon, and then the body of the loop in here, I'll just put a comment there, code the body of the loop. But at the end, the tail of the loop, the thing that causes it to loop again and again some specified number of times would be these two lines, dec RCX and jump not 0 main loop. It doesn't have to be RCX, it can be any register or variable there, but yeah, that's what you see at the tail of the loop. Dec something and then jump not 0. Good stuff. Decrement, number 10. Okay, number 9, here we go. So we're getting to the top 10 now. This is comparison instruction. So the compare instruction is, funnily enough, used to compare two operands, and it sets the flags to indicate what it found out about them. This is how we get the CPU to do conditional things. Yeah. So for instance, if the two operands are equal, the CPU is actually going to set the 0 flag. And after a comp, we can perform any number of different instructions which read those flags. So there's a bunch of conditional jumps, a bunch of conditional sets, there's conditional moves. Yeah, which each read the flags that the comp instruction sets. So a lot of other instructions also set the flags, and you can perform conditional operations after them, but comp is sort of an explicit way to set the flags. Actually, the instruction performs a sub. It performs a subtraction of the second operand from the first, and it sets the flags, but it doesn't save the result in the first operand, unlike sub. And it's really, really important and really confusing as well, but you've got to remember what the results actually mean in terms of operand order. So, yeah, just a little example down here. I always get this mixed up, but the following code jumps if EAX is less than 5, not if 5 is less than EAX. Yeah, come to EAX 5 and jump less to some label. Yeah, just be careful of that. It's easy to mix them up. Alright, number 8, here we go, the bitwise OR. Or Boolean OR. Okay, so this is used to perform the bitwise OR operation, sometimes called Boolean OR, between two operands. And the OR operation actually sets bits to 1 in the destination if either of the two operands have 1 in their corresponding bits. So the truth table for OR is as follows. It returns 0 if both bits are 0, otherwise it returns 1. Yeah, really, really important. I mean, these Boolean operations are arguably the most powerful of all, since with the shifts and the Boolean operations, you can actually get all of the other operations, anything from multiply, you can get divide or add, you can get anything at all really from the bitwise or Boolean operations. Anyway, there's the truth table for all. Okay, so number 7, bitwise AND. Bitwise AND is really, really important as well for masking stuff out of registers and different variables. The bitwise or Boolean AND operation returns 1 only if both bits in the operands are 1, otherwise it returns 0. Something you'll see the compiler do, I think the compiler does this actually, am I using it? Yeah, I think it uses AND, but a really common trick to check if a register is 0 is you AND it with itself. So something like AND RAX is going to set the 0 flag if RAX is 0, otherwise it's not. But the important thing is it's not actually going to change the value of RAX. Yeah, have a look at the Boolean instructions, I think, elsewhere if you're a bit unsure as to how they work, because I haven't really mentioned it here, but you've kind of got 8 bits of one operand and 8 bits of another operand, and the bitwise AND is performed sending style between all of the corresponding bits. It really was confusing. You might also, this is an honourable mention here, you might look at the test instruction, which does exactly the same thing as AND, but it doesn't set the results in the destination operand. Yeah, so test is a bit like a bitwise version of the compare instruction. Here's the truth table for AND down here. So, like I said, it returns 0 for every situation other than the one where both operands have 1s. Yeah. Okay, number 6, bitwise exclusive OR. So this isn't one of the original Boolean operations. The Boolean operations were only not, and OR, but exclusive OR is used a lot in computing. So it's another bitwise operation with its own truth table. And it can be seen as one or the other, but not both. Yeah, so if either of the operands have a 1, then the answer is 1, so long as both of them don't have 1. That was a hopeless way of describing XOR. An easier way to describe XOR is not equal to. Where it's not equal to. What it does is sets the bits to 1 based on this truth table down here. Yeah, so if operand 1's bits are not equal to operand 2's bits, then they get a 1, otherwise it's a 0. So what you can do, and this is really, really common, you can 0 a register with XOR. So XOR EAX is actually going to copy 0 into EAX. For some strange reason, it's still faster on modern mode than mod EAX is 0. Yeah, weird. Anyway, I don't like rules. Here's the truth table for XOR. Yeah, this will show you really why that XOR thing works up here. Yeah, XOR and then the same parameter twice. It doesn't matter what the bit is in EAX, it's either going to be a 1 or a 0, but whatever it is, they're going to result in 0. Yeah, so both operands of 0 results in a 0, both operands of 1 results in a 0, and we're comparing the same operands, so they're never going to be different. Anyway, bitwise exclusive OR, number 6. Here we go, number 5. Jump. Yeah, I've sort of teased you my list here, and I've included all of the conditional jumps and the unconditional jump as a single, number 5 in my list. The jump instructions are used to branch or change the current IP. Yeah, you can't actually say something like, mod IP some label. That's illegal. But jump some label is exactly the same. That's what it does. We're really moving something into the instruction pointer. Yeah, and you can use a register or a label. I think actually for the JCC you can't use a register. Yeah, that's a lie to say, sorry about that. But there's a multitude of different jump instructions. JMP by itself is unconditional and it always jumps the IP to the operand. Otherwise, we specify some condition which is based on the flags register. Yeah, so the JCC is just here. You replace the CC with some little condition code, and it means read the flags register and jump based on the condition. Any JCC is going to fall through if the condition is false, otherwise it's going to take the jump and jump to the label. What you want to do is perform a comp or a compare, and after that some conditional jump, so that you can compare two values together and jump based on whatever you found. Some of the most common JCC mnemonics here are JZ for jump 0, or JE sometimes that's called, jump equal. JNZ for jump not 0 flag, or JNE that is in other words. So JZ and JE are the same, and JNZ and JNE are exactly the same as well. Or you've got jump less and jump greater for signed comparisons down here, and the corresponding unsigned versions will be jump below and jump above. I don't know who decided that jump less meant signed and jump below means unsigned, but it's just something you've got to get used to, really. It's what the x86 instruction set does. Alright, number 5 is jump. Number 4, here we go. We're getting into the big guns now. This is super, super important. I mean, I don't know how much you can do without using subtract, but number 4 on my list is sub. Subtract is used to subtract the second operand from the first and store the result in the first operand. It works for signed and unsigned due to the magic of 2's complement binary numbers. And a lot of the reason why x86 actually uses 2's complement is because subtract and addition are so easy on 2's complement numbers. Anyway, we're not talking about that, but subtract sets the flags in exactly the same way as compare. Yeah, like I said before, so compare is actually going to perform a subtract, it just doesn't say the results. What you want to remember, yeah, this is really important. You always want to remember that the second operand is subtracted from the first, not the other way around. Some instruction sets actually have a reverse subtraction, which does the opposite. But subtract does subtract that second operand from the first, and store the result of the first. Number 4, subtract. Here we go. Number 3, add. Okay, yeah, well, we're not going to get very far without adding variables at some point, so you've got to learn the add instruction if you're interested in assembly. Add is used to add the source operand to the destination and stores the result in that first operand. It works for signed and unsigned numbers equally well. Once again, that's due to the really clever system that we use called ca1015. Have a look, it'd be interesting. Add, yeah, number 3. All right, number 2, here we go. So things are really getting very, very useful. This is, I think, one of the most interesting and useful instructions in the whole instruction set. I think it's number 2, actually. Yeah, second from the most interesting of all. It's a load effective address, LEA, LEA. Apart from having rather a pretty name, it's used to load an address into the destination operand. The destination operand effectively becomes a pointer to the second operand. So you might do something like, say you've got a variable named sumVar, LEA, RAX, and sumVar in square brackets is exactly the same as point RAX to sumVar. So then, RAX is just a pointer, you can change sumVar however you like. And what's really interesting about load effective address, apart from this, obviously fundamental ability to load pointers into registers, but it's actually really useful as a really fast arithmetic instruction. So I made a shoot about this not long ago. If you want to have a look at some really interesting multiplication and addition tricks with LEA, maybe I'll figure out somehow to put a link in this video somewhere. I'll also put a link in the video description. Yes, maybe. Number 2, load effective address. And here we go, drum roll. What's number 1? The single most important instruction that every assembly programmer should know. Move. Mov. The humble move instruction. Alright, so I reckon that this is probably the first instruction any coder should learn. So despite its name, move doesn't actually move data, it copies it. Yeah, so move would imply that it takes the data from the first and puts it in the second. Probably zeroing. No, other way around. It takes the data from the second and puts it in the first. But actually move performs a copy. Yeah, it won't take the data out of that second operand, it keeps it in the second operand and copies it to the first. Move or mod is actually the most common of all instructions, according to that list that I showed you earlier. The move instruction accounts for about 20% of all x86 code in the world. So it holds a standing position in part due to the fact that x86, rather annoyingly, doesn't have non-destructive instructions. Yeah, if we could actually save the results of, say, an add or a sub to some third operand, I don't think move would be anywhere near as common as it is. But as it stands, about 1 in every 5 x86 instructions will be a mod. Super, super important. Another trick that you might see, if you look at the compiler's code, the C++ compiler's code, you'll see over and over again this rather strange thing. It's got mod, EAX, EAX. And why would the compiler move EAX into EAX? What would be the point in that? But there is something strange that mod does with 32-bit operands, and that's that it zeros the top 32 bits of RAX. Weird. Yeah, so if you ever want to zero the top 32 bits of one of those 64-bit registers, what you want to do is mod, and then the 32-bit version has both operands. Anyway, number 1 on my list is move or mod. And that's the end. So these 20 instructions cover just about all of the x86 in the world today. I think it's super, super interesting, but these instructions have pretty much been with us since
Alright,
the
so I
70s.
just made it up for hitting you too hard.
These instructions come from the very first x86.
Have a good study week, and there you go, I'll be glad to.
You have been on the web courses.
This is on web course. I'm hoping that you guys do really well on Monday. I think you will. We're making some time.
Yeah, you get so